So these are the anti-differentiation rules that we have been introduced to. I actually gave them to you in chapter 5, and I said at the time, if you go back to your chapter 5 notes, it says, integration rules from 6.2. So here it is. For some reason, the book puts this in after, but it doesn't make sense. So remember, we have the power formulas, right? So basically, this is when I'm integrating x to the power of 3 or something like that dx. And what happens is I add 1 to the exponent and I divide by the new exponent plus c. That works for any power, whether it's positive or negative, even 0, except if the exponent is negative 1. That's the one case where that power rule doesn't work, because if the exponent is negative 1, then it's 1 over x dx, which doesn't go with the power formula. That's just ln of x plus c. Okay? Okay. So next we have the trig formulas. You have to know all of them, right? 99% of the time. Okay, so so cosine, right? The integral of cosine is sine. And remember, this case, right, where the integral of the sine is the negative cosine, right? And so remember that it's because if you're trying to go backwards, the derivative of cosine has opposite sign, right? So you have to put a negative in front of here, right? Whereas the derivative of sine is cosine, so that's how it works, right? Okay, next we have the derivative, integral of secant squared is tangent. Secant tangent is secant, right? These are the ones that show up 99% of the time. Does that mean you don't need to know the other two? Absolutely not, okay? And so you see, however, that, you have these two, secant and secant tangent, and they follow the same pattern for the cosecant except with the negative, right? All right. Another favorite, integral of e to the u is e to the u plus c. These are pretty much the ones that are, like, they have the potential to, fool students, because you have the integral of 1 over 1 plus u squared. That's an algebraic function, but the integral is an inverse tangent, right? It's a trig function. And here, again, algebraic, but that. How do you recognize these? You just have to learn them and recognize them. But basically, it's a huge downfall, right? It's like a pitfall for students where they see this and immediately they think there is going to be an algebraic integral, but no, it's inverse sines and tangents. So remember that. Okay, we've done all of these, but we have not yet had composite function. It's just been sine of x, ln of x, and so on and so forth. Okay? Yeah. Huh? We don't deal with that. It looks like this, but we don't need to deal with it. Okay. Okay, so now let's talk about composite functions for a minute, and let's talk about how we found the derivative of e to the 3x versus just e to the x. Do you remember that? What we did, right, for e to the 3x, we said, okay, the derivative of e to the anything is e to the anything. But now, to account for the composite function, to account for the stuff inside, we then had to take the derivative of 3x and say times 3. So this would have been 3e to the 3x, right? So you have to take a derivative of the outside and then of the inside. Same thing here, right? What is this? ln squared x. That's just ln of x squared, right? So first we took a derivative of the outside, right? It's something squared. So that was just 2 ln of x to the power of 1 times the derivative of the inside, 1 over x, to give us 2 ln of x over x. Right? This is a composite function. Look at this next one. Instead of just cosine of x, we have cosine of x squared. One function inserted into another. The derivative of the outside function is what we do first. And that gives us a negative sine x squared times now the derivative of the inside, which is 2x. So that gave us negative 2x sine x squared. Okay? So you see how, there was like a process by which we had to account for the nested function. So now, if I had to go backwards, right, I have to do the same thing, right? So look at this top one. To go backwards, if I were to integrate 3e to the 3x, if I wanted to integrate this and get the original function, I have to have a way of eliminating the stuff from the inside in order to get back to the original function. So how do we do this? So what does it look like when we have to integrate a composite function? So first we have sine of 2x, right? You see how this is different from integrating sine of x? We now have sine of 2x. In this one, no. So this is like 1 over x, but now I have 1 over a different function, right? 2x minus 1. This might look like e to the x, the integral of e to the x, but I have this 4x that complicates things. Here, this should have a parenthesis here. This looks like a power rule, something to the power of 4, but inside I have a 3x plus 5, right? So what we have to do in order to integrate these is called the substitution method. All this is doing the chain rule in reverse. So here is how it works. If f of x is the derivative of capital F, right? So little f is the derivative of capital F. Then, let's put the parentheses in the right places here. U prime of x. Okay, so then, capital F of u of x, and yes, that says f of u, that's fine, okay? We get over it very quickly, right? What is that? That's the integral of f of u times u prime. Okay? So what are we doing basically? We're integrating, right? The function and then the derivative of what? The inside, right? So that's what you have to do. You have to integrate the function times the derivative of the inside. Okay? All right. And what is little f? It's the derivative. So let's do it. So let's see how we do u substitution. It's called u substitution. This is the lingo for it. It's called u substitution. So what we do is this. Again, we have to figure out outside function and inside function. Usually, this is the hardest part, is figuring out what those are. So u is going to be the inside function, right? So if you have f of g of x, this inside function is u. Okay? So for example, if I have something like this, 4 times 4x minus 5 to the 6, from the outside, it's something to the power of 6. So the inside function here is u. Okay. So first you have to identify u. Then you have to find what we call du. So if u is 4x minus 5, du is what we call the differential. What is the differential? It's the derivative of u multiplied by dx. That's the important part. Okay? Very quickly, you figure out that if you forget that dx, everything goes wrong. So if u is 4x minus 5, du is the derivative of this, which is 4 times dx. So if it starts with du, it must end with dx, right? Because why? Why is it that way? Because how do I take a derivative of u? It's du dx, isn't it? Du dx is 4x minus 5. So then what's du? 4x minus 5, du is just 4, right? So what's, okay, let's start that again. I'm sorry, I have a very bad headache. What's the derivative of this? It's du dx. And the derivative is just 4. If du dx is 4, du is 4 dx. So du is 4 dx. Okay? Okay? All right. Next, what you do is this. Now we have to rearrange and rewrite the integral in terms of u. Okay? Here's what you do. What did we say u was? This we said was u. Cool? Okay. So, I'm going to rearrange this. So look at this. I move the 4 over here in front of the dx, right? Why? You'll see now why. This inside we said was u, correct? And what did we say is 4 dx equal to? Du from up here. So now I have 4x minus 5, that's just u to the 6 du. Okay? What have I done? I've substituted, and then what did I do? I no longer have the original variable in my equation. All right? I know this sounds a little confusing, but we'll do it right now. So now look at what I have, though. I have a totally simple function that I can integrate. If you have the integral of something to the 6 du, can you just integrate? It gives you u to the 7 over 7 plus c. And that's it, right? So now my integral is u to the 7 over 7. But I can't leave it like that. What was u in the beginning? What did I say? It's 4x minus 5 to the power of 7 over 7 plus c. And that's the integral of that. Here. Yep. Okay, so that's how we account for all that. So now, let's do this one. For the first few, I'm going to give you the u's, and then nobody gives you the u's, right? Okay, so let's do this. You only understand by doing. Okay, so I have x minus 7 cubed. The inside function is your u, which in this case is x minus 7. Okay? So now what I do is I say, okay, what's du? It's the derivative of this, which is 1 dx. Right? So du is just dx. Yeah. Like, for instance, if you got u to the 7th over 7, are you allowed to leave your answer like that? No. You can't. Okay, so now I'm going to rearrange my original integral, but eliminate all x's. Only u's should appear, u's and coefficients. So this x minus 7, that was u to the 7. What's left? Dx is left. That's 3. What's left here? It's dx, right? Well, how do I substitute dx? I go here. Dx is just du. Okay. Now I integrate u to the 4 over 4 plus c. But now I need to put the original u back in here. So it's x minus 7 to the 4 over 4 plus c. Okay? Let's do another one. Okay. Let's do another one. Huh? Where? Okay, so B is a little different. So here's what we're going to do with B. You look at the more complicated part of this function here. 2x, x squared minus 1. Definitely there is a lot more action with this root than with the 2x, correct? So you go to the more complicated part of the problem, which is the square root, and then you go inside. So you take the inside of that complicated part. So this is going to be my u. Okay. Du is the derivative of x squared plus 1, which is 2x dx. Okay, now, I go here. All right. This, all right, we have the square root of x squared plus 1. That's a u. Okay? So now I've accounted for the square root. What have I not accounted for? The 2x and the dx. The 2x and the dx. But, oh my God, what is 2x dx? Look at this. What is 2x dx?
Wow.
It's du. Hang on. 2x dx is du, right? So for the whole thing, I just substitute du. Now, sometimes it's just that easy. It's just that convenient. It's just like, straight substitution. Sometimes I might have to manipulate this du dx in order for it to look like this. Okay? But no matter what, if you've chosen the correct u, it's like a puzzle. It'll all fit. Okay? So you know how when you're doing a jigsaw puzzle, you get to a point where you're like, no, there's no way. There's a piece missing. There's no way. There's a piece missing. But then if you do everything correctly, you're like, oh my God, like it's magical. They all fit. That's what it is here. Sometimes you may feel like, this isn't going to work. This integral doesn't work. You've either chosen the wrong u or you're not manipulating properly. Okay? Never lose faith in the process though. So now, this we've been integrating forever, right? This is just u to the half, isn't it? So when I integrate, it'll be u to the 3 over 2, half plus 1, times 2/3 plus c. If you leave it here, half credit. If that, I don't know, it depends on how many points. You must substitute correctly and say this is 2/3 x squared plus 1, 3 over 2 plus c. This is where it gets fun, right? The integrals from chapter 5 were boring. This is where all the action is. Okay. No. It's indefinite for now. Definitely not indefinite though. Okay. Okay. All right. So, this one, again, You have a 2x and then blah, blah, blah to the fifth. That's the complicated part of the problem. You go to the complicated region and then you go inside, right? And you choose that as your u, okay? And so du will be 2x dx. So now you have the integral u to the fifth. And look, 2x dx, that's just du. So now I can integrate this. U to the 6 over 6 equals x squared plus 9 to the power of 6 over 6 plus c.
And taking du of du to get something dx, is that just a substitution for the sake of getting it to u?
Yes.
So
yes. Yeah. Okay, let's do one more. Here I have sine of x, e to the cosine of x dx. So again, where is the more complicated region? It's e to the, and then you go to the inside, so what do you take? Cosine. All right? So du is how much? Negative sine x dx. Okay, so now look at what's going to happen here. Here I have e to the u. Now, what do I have left? Sine x dx. So now this is the important part. I have to go here to my du, and I need to solve this for the blue parts, sine x dx. So here, sine x dx is equal to what? Negative du. So when I go in to substitute, it's negative du. You see that? But what the heck is that? We don't do that. So that's the same as negative e to the u du integral, which is negative e to the u plus c, which is negative e to the cosine x plus c.
It's negative e to the u du is the same as like the integral of negative e to the u?
Well, yeah, the negative is outside.
But you wouldn't just put it like before the e?
You could have put it in here. It would still be negative e to the u. Yeah. Okay, let's move on. 5 plus 2x cubed, right? That's going to be the u. Again, it's inside that root and so on. So du is 6x squared dx. Okay, let's see what's going to happen here. I have here the square root of u. Now, what do I have left? X squared dx. So what's x squared dx here? Right, 1 over 6 du is x squared dx. So here's how I do it. The 1 over 6 du can be split up, right? They don't have to be stuck to each other. So I can put 1 over 6 out here because it's a coefficient, and du over here. When I took a derivative here, 3 comes down, so it's 6x squared dx. C is a constant. It could be either a 2 or a negative 5. We don't know, so it's always plus C. It's a generic plus C. It's still C. Yeah, it's still plus C. Yeah. All right. So here it's going to be 1 over 6 u to the 3 over 2 times 2/3 plus C. You see how I combine steps? And so at the end of the day, this is going to be 1 over 9. U is 5 plus 2x cubed to the 3 over 2 plus C. Fabulous. Look back there. I know. All right, here. Now we have to choose our own U. So what do you guys think for the U here? 4x plus 3. So, no, you have to have chosen the right U. Otherwise, it all fails. U is 4x plus 3. That means du is 4 dx. So, here, I have u to the 4. I've got dx left. And when I go back here, dx is 1 over 4 du. So it's 1 over 4 du. So this is 1 over 4 u to the 5 over 5 plus c, which means 4x plus 3 to the 5th over 20 plus c. Okay, right, so this next one is one of my favorites. You have ln to the power of 6x. This is just ln of x to the 6. So what would you take as your u? ln of x. Du is what then? 1 over x dx. Okay. What have I got here? ln of x to the 6, that's u to the 6. What have I got left? Dx over x, right? And what's dx over x? Here. That's just du. You see how nicely it all fits together? So u to the 7 over 7 plus c. ln of 7 of x, ln x to the power of 7 over 7 plus c. One thing I want you to pay attention to, all right, is this. Notice, some of you guys are getting a lot better. Some of you guys still have a way to go. Notice the equal signs in between each step, right? They're not just random, like unrelated steps, right? Equal signs in between each step. That's important. Also, look at the C. I don't wait until the last step to put the C in there. You have to put it at the very beginning before you even substitute the U back. Okay? Okay. What about this one? What do you think for the U? X squared plus 3. So du 2x dx. Okay. So now, what do I have here? I have here something 1 over basically the square root of u, right? And then I have x dx. What is x dx from my u? Right. Half du is x dx. So half du. Okay. How am I going to integrate this? This is u to the what? Negative 1/2. So I'm going to have half times u to the power of positive 1/2 times 2 plus c. So all I got, because it's like dividing by a half by the new exponent. So it's the square root of u plus c, the square root of x squared plus 3 plus c. Okay, parentheses look like this here. Okay, so what would you choose as the u? It makes all the difference, yeah. X cubed plus x.
So if you have that, or if you get that on the test, it's the one with the higher exponent.
Right. Yeah, it's the more complicated one, yeah.
It takes more to
So it would be like, even if it was like to the negative 3 over 2, like you would still take x squared, like the one which is
That's debatable. You would have to like try, right? Like if they're like the same level of complexity, you know. Okay, so x cubed plus x du is 3x squared plus 1 dx. Look at what you got, right? You got this. Isn't that cool? So here is another telltale. Sometimes you can even, just by looking at it, recognize, hey, look, one of these is the derivative of the other one, right? And that already tells you that the non-derivative is the one that you pick for your u. Okay? All right. So now I have u squared, and then 3x squared plus 1 dx, that's just du. So u cubed over 3 plus c x cubed plus x over 3 plus c cubed, sorry.
So when we multiply like how the c we multiply by 1, we did that because we're trying to get when we read out something like how that would be x times dx, we're just trying to get that, and so whatever it doesn't just get that.
Exactly. Yeah, like if you go here, right? X times dx, that's what you need, right?
Yeah.
If you solve it for that, x times dx is 1 over 2 du. Yeah. Yeah. Yes.
So just like on the subject of like choosing correctly.
So, shortcut. You could only do this if the derivative of u is a constant. So for example, if u is 2x plus 5 and the derivative is a constant, if the derivative, right? Then, so only if the derivative of u is a constant, then what you do is, to integrate, you just integrate and then you divide by the derivative of the inside. But it only works if the derivative of u is a constant, right? So for example, look at d, right? U was x cubed plus x. Du is this hot mess. That's not a constant. You can't do it. Could you have done it for b here? No. Could you have done it for a? Yeah, right? That's the only case that you could do it. So, like, look at this one, for example. What would you have chosen for the u? It would have been 2 theta. The derivative of that is 2. So you don't have to go through this like long-winded process. You could just say, okay, the derivative of cosine is sine of 2 theta divided by 2 plus c. Okay? Yeah. Same thing here. U would have been 6x, the derivative of which is a constant. So now you say, okay, integral of e to the 6x is e to the 6x, but divide by the derivative of 6x, which is 6 plus c. What would be the u in this case? 4x minus 1. What's the derivative of it? 4. So I just take this and I integrate to the power of 4 over 4. Now you divide by 4, right? Plus c. So it's 4x minus 1 to the 4 over 16 plus c. Cool? Okay. All right. Now, definite integrals. So, let me just do that. Okay. Yeah, that's a handout. If u of x is differentiable on a comma b, right? They all have to be differentiable in order for you to take an antiderivative, right? And f of x is integrable, then if you have the definite integral of something like this, what you can do is you change, once everything is in terms of u, right? Like this one. Where is it? Once everything is in terms of u, you change the bounds so that a becomes u of a, b becomes u of b, and then you integrate that way. What do I mean? Let's do one. So here we're going to make a u substitution and integrate. All right? So here's what we're going to do. First and foremost, we integrate just like we were doing before. What is going to be the u here? U is x squared minus 4. Ugh. That means du is 2x dx. So let's do this. This is going to be 1 over u. And then x dx is what we need, right? So 1/2 du is x dx. So 1/2 du. Okay, hang on. Now for the bounds. Okay. These bounds here from 0 to 1 were for the x's when your function was x over x squared minus 4. Now I have a completely different function, 1 over u. So if my x's went from 0 to 1, u can't go from 0 to 1. It has to go according to its function. So what do I have to do? I have to find u of 0. So plug 0 into the function u. 0 squared minus 4 is negative 4. So that goes here. U of 1 is 1 minus 4 negative 3. That goes there. Now I've changed my bounds to u. And now I can integrate and use those values. So let's do that. This is going to be 1/2 ln of absolute value of u in brackets from negative 4 to negative 3. You see how important those bounds are, those absolute value bars are, right? Because my bounds are negative. I'll take questions in a second. So this is 1/2 ln of 3 minus ln of 4. So now look at this. This is 1/2 ln of 3 over 4. But what happens to the 1/2? It comes up. So this is ln of root 3 over 2. Remember all those logarithm properties? Yes, 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 yes. So that's it. Now, before I take a question, one more thing. Huh? No, because what happens is here it's ln of root 3 over 4. Okay. You could also not put the bounds. Integrate, change back to x, and then use the bounds for the x. Both will work. I used to do it that way, like the first half of my teaching career. I do it now. Maybe like in another, couple of years, I'll change back. It really makes no difference. Maybe this is more straightforward. I don't know. It's all the same to me.
So you would just do,
okay.
You do 1 over x squared minus 4.
Correct. No, it'll be like ln of x squared minus 4. Here, it'll be ln of x squared minus 4 from 0 to 1. You get the same exact thing. Okay, question.
Do the bounds have to be separated by the same difference as the x? So the bounds
No.
Same difference.
It depends on the function. No.
It's just a
Nope.
coincidence.
Yep. Big time. Especially if like it's tangents and stuff, right? Then it's a whole other situation. Okay, what's gonna be okay? Here we go. Here is a test now. What are we gonna take as the u? Okay, secant x, but then what's the u?
Because secant x squared.
No, I do tangent x
squared.
because derivative tangent is secant.
Is it secant x tangent x?
The u is secant x.
No, because the secant the entire thing is secant squared x.
No, he's right. No, it's tangent x because the
the only thing
derivative
that
of
will
tangent
cancel
x
them out.
becomes secant squared.
If you don't do tangent x, I just tried it.
So you have so the derivative, the u here has to be tangent x because du is secant squared x dx. If you do it the other way, it actually does not work. Okay? Because if you do it the other way, then if you have secant, then the derivative is secant tangent and you don't have enough secants to go around. So this one here, it's going to be the integral of basically u du. You see how simple it turns, like what a simple function it turns into? So now what about the bounds though? The bounds, it's going to be u of 0, which is tangent of 0, 0. U of pi over 3, which is tangent of pi over 3, which is root 3. Root 3. That's the bigger angle, so it's root 3. So now I have u squared over 2 from 0 to root 3. Root 3 squared is 3 over 2 minus 0. And that's just 3 over 2. Okay. Is it possible to do this one? What's the u here? 9 plus x squared. All right. So let's do it. So now, if you take, what would you take as your u? Okay. So then what would du be?
2x, which doesn't cancel.
2x. But is there another 2x here for you to cancel out? Mm-mm. So now what? You have to do what?
Oh,
You do
you have to
9%
factor.
squared and then you have to do
Tangent inverse. This is tangent
So
inverse.
you can divide this by 1 over 9. Divide this by 1 over 9. Okay? I'm sorry. Multiply by 1 over 9. Basically, divide 9 from both top and bottom. So what you end with here is 0 to 3. In here you have dx. And in here you have 1 plus 1 over 9 x squared. Is that right? But is that the same as x squared over 9? Dx? Yeah. Oh, wait, I already have the dx there, sorry. Equal to. Look at what I have here now. From 0 to 3, 1 over 1 plus x squared over 9. I can rewrite it as x plus 3 squared. And I have the dx out here. I just rewrote it. I put the dx out here, so it's 1 and then dx out here. And here, 1 plus x over 3 squared. Okay? What is that?
Tangent inverse.
That's the inverse tangent derivative, right? Look at this. Yep. Max did call it. This is what I mean. You get a function that looks like an algebraic function, but it takes a while for you to recognize 1 over 1 plus blah squared is inverse tangent. So this is, oh my gosh, we're running out of time. Let's hustle here. So this is inverse tangent, except I still need a u here. So what's the u gonna be? X over 3, which means du is 1 over 3 dx. So now,
Can you do the shortcut?
let's not, because this is turning out to be rather complicated. So now I have 1 over 1 plus u squared du, right? What have I got left? Dx. So what's dx? It's 3 du. So 3 du. Now, I need u of 0, which is 0. I need u of 3, which is 1. Now, this is 3 inverse tangent of u from 0 to 1. So this is 3 inverse tangent of 1 minus inverse tangent of 0. So this is 3. What's inverse tangent of 1? Pi over 4. What's inverse tangent of 0? 0. So that's what we have, 3 pi over 4. Okay? Homework is a handout. Let me give it to you.